Hi all, welcome to our week 2 video. This week we're talking about probability and probability distributions. We're going to start this video with some key terms and how to calculate probability in general. Let's start with a definition of probability. So probability is a measure of the likelihood of an event occurring. For example, you see this in everyday life, right? You see this as 30% chance of rain. We know when we talk about flipping a coin, there's a 50-50 chance you're going to get a heads or a tails. So you're probably familiar with probability in everyday life. We're measuring the likelihood or the chance that some specific outcome of interest is going to happen. So an outcome, when we use this in statistics specifically, means a single specific result of a probability experiment. So for example, if I'm talking about flipping coins, flipping a heads is a single outcome, one thing. A probability experiment is anything that's governed by chance. The sample space is all possible outcomes for that experiment. So if I'm rolling, for example, a 6-sided die, then I have 6 possible outcomes in my sample space, the numbers 1 through 6. An event is then one or more outcomes. I can have a single outcome. We would call that a simple event. Flipping a heads, rolling a 1 on a 6-sided die, drawing the Queen of Hearts from a deck of cards. We can also have compound events, events that have more than one outcome in them. If I'm rolling a 6-sided die, for example, rolling an even number is compound. That's 3 separate outcomes, a 2, a 4, or a 6. We're not going to worry about it too much right now, but as we move through this unit, we're going to learn that compound probabilities usually require some nifty math tricks to calculate. What we're going to focus on today is how to do the calculation for a single outcome or a simple event. And that's going to depend on the type of probability that we're interested in. There are 2 types of probability. The first is theoretical, and this is based on our understanding of the statistical system that we're looking at. So for theoretical probabilities, we can go straight to the calculation. We don't have to collect any data. We already know how the system behaves. So flipping coins, rolling dice, drawing cards from a deck of cards. These are all things that we know what the system looks like and how it behaves, so I don't need to do any experimentation to calculate my probability. So for example, if I flip 2 fair coins, I want to know what the probability that both coins land head up. So to calculate this probability, our probability is the number of ways to get the event that we're interested in divided by the total number of outcomes in our sample space. So we're going to do this for our example. If I flip 2 fair coins, I have 4 outcomes. So my sample space for my example would be, I could flip 2 heads, heads. I could flip a heads and then a tails. Whoops. I could flip a tail and then a head, or I could flip 2 tails. So what I've done right here is I've listed my sample space, all of the possible outcomes from my experiment. And I can see there are 4, so the bottom of my probability fraction for this problem is going to be 4. Then I need to figure out what is the event that I'm interested in. And this example says, what is the probability that both coins land on heads? So looking in my sample space, this is the event of interest. That's both coins being heads up. So for my probability fraction, P both heads, the top number is the number of ways to get both heads, which is 1. The bottom number is the size of our sample space, which is 4. So if I repeatedly flip 2 coins, I expect about a quarter of those outcomes to be 2 heads. There's a 1 in 4 chance when I flip those 2 coins that I will get 2 heads. The other type of probability is called empirical, and this is based on data. So we'll do an example here. It says Natalia created an 8-sided die using her school's 3D printer. To test whether her die is fair, she rolls the die 100 times and records the results. Find the following. And we're given 4 probabilities. What's the probability that you roll a 7, you roll an 8, you roll an even, or you roll a not 1? So first let's look at that probability. So for empirical probability, to calculate that probability, we're going to build a fraction where the top is the class frequency. How many times did that specific outcome occur? And the denominator is the total frequency. How many times did we perform the experiment? So we're going to use that for these 4 problems. So let's start, and I'll color code, with 7. So I want to know the probability that I roll a 7. I go to the table, I look at where 7 is, and I can see that a 7 was rolled 24 times. And I was told, back at the top, that we rolled the die a total of 100 times. So my probability here should be 24 over 100. You have a couple choices. Your book is generally going to leave it as an unreduced fraction so that you can check your work easily. As a practicing statistician, it's proper to reduce the fraction or to state it as a decimal answer. So if I wanted to reduce this, I can see that both of those numbers are divisible by 4. So in the numerator, 24 divided by 4 is 6. Somebody check my math. And I know that 100 divided by 4 is 25. So there's a 6 in 25 chance of rolling a 7. And let's go ahead and do the same thing for 8. So to roll an 8, I go to the table and I look for the 8 class frequency, which I can see is 6. And then I build my probability fraction. 6 ways to get an 8. 100 total outcomes, total frequency. And in this case, top and bottom are divisible by 2, so this I think should be 3 over 50. We're going to do the same thing for even and not 1, and we're going to have to think carefully about these because these are no longer single events, these are compound events. So let's go ahead and do even in blue. So I'm looking for all of the even numbers. And those even numbers are 2, which has a frequency of 9, 4, 6, and 8. And I need to add those up. So 9 plus 14 plus 15 plus 6. So 9 plus 14 is 23, 38, 44. Please send me an email if I made a boo-boo. Over 100 as our total frequency. These are also both divisible by 4, so 11 over 25. And we can see that getting an even number is more likely than getting a 7, because 11 25ths is bigger than 6 25ths. All right, for the last one, we want a not 1. And there's 2 ways to do this. I'm going to do it both. So the first way is to look at all the outcomes that are not 1. And that would be a 2, 3, 4, 5, 6, 7, 8. And just like last time, I'd have to add all those up. So 9 plus 12 plus 14 plus 10 plus 15 plus 24. I'm running out of space here. Plus 6. I'm going to start at the back end. 6 plus 24 is 30. Plus 15 is 45, 55, 69, 81, 90. That's up to 90 out of 100, which is 9 out of 10. However, there is a faster way to get this. I am lazy, and I can see that everything in the table is 1 through 8. Not 1 is 2 through 8. I know the whole table has to add up to 100% or 1. So another way that I can do P not 1 is to do the total, 1 or 100%, minus the probability of 1. And if we check that, 1 minus and the probability for 1, I can see there's 10 ones that occurred out of 100. So this would be 100 100s minus 10 100s, which is 90 100s, which is exactly what we got the long way. 9/10. This trick here is called the complement trick because this, not 1, is a complement to the event 1. And Notice it's spelled a little bit differently. This is not a compliment like somebody telling you your fit is fire today. This is a compliment to a statistical event. Okay, before I let you go for this video, one quick note. We're using something for probability that looks like notation you probably saw in algebra. This looks like function notation. So it's really tempting for students when I'm finding the probability P1 equals what, I will often see students put the answer in the notation. And this is not what we want to do. To be very clear, if I have px equals 25, this thing here is the event that I'm interested in. Not a probability, an event. Sometimes it'll be a number like it was for our dice. Sometimes it'll be a word like even. This is the answer. This is our probability. Except I can't spell today. So probability notation goes on the left. It's telling you P for probability, and then the thing in parentheses is the thing you're finding probability for. Your answer goes on the right. All right, if you have any questions, feel free to send me an email or drop by office hours. Otherwise, I'll see you in the next video.